First off, I need to apologize to you guys. I accidentally, in the quiz I gave you over the weekend, I did make an error in the second question. And I do want to kind of go over it real quickly because I do think it's something worth seeing. So let me show you guys the error I made was as far as the grading, you get credit for doing it either way, but I will definitely post solutions to this to kind of get at what's going on here. So let's go ahead and look at problem 2 from the quiz I gave you guys. So, excuse me, sorry. You were given the following, that x of t, y of t had the general solution c1 e to the minus t times 1, 1, c2 e to the minus 2t times 4, 5. So this was the general solution to a system of equations. And the initial conditions were that x of 0 and y of 0 were equal to 1, 0. So this first part wasn't an error. You could totally do this first part. You'll want to find C1 and C2. To do that, you're going to say that, so to find C1 and C2, you're going to set t equal to 0. And if you set t equal to 0, you're going to get 1, 0. Equal to C1 times 1, 1 plus C2 times 4, 5. So then you got to solve for C1 and C2. I'm going to say 1 equals C1 plus 4C2, and 0 equals C1 plus 5C2. I would probably subtract these equations. 1 minus 0 is 1, C1 minus C1 is 0. And 4C2 minus 5C2 is negative C2. So let's say C2 equals negative 1. And then C2 equals negative 1. It looks like C1 has to equal, let's see, 1 equals C1 minus 4. So C1's got to be 5. That part's perfectly fine. Again, for those of you that just came in, I'm looking at problem 2 from the quiz I gave you guys over the weekend. Oh, I should pin my video. So we found C1 and C2. Now we're going to look at the second part. And so the second part, I made a mistake. I said that the system's equation was actually something that wasn't. So the system of equations should have been dx dt equal to, when I wrote it down here, now I've, 3x minus 4y, and dy dt is, where'd you go? Sorry, 5x minus xy. So in the quiz, I accidentally had a positive 4 there. I'm sorry for that if it caused you any confusion. But yeah, well, let's go ahead and do at least part 2b, because actually you still could have done 2c and it should have worked out okay. 2b wouldn't have worked out because it was dealing with this first equation, which was wrong. So let's look at what 2b is asking us to do. So 2b asks us to do the following. First ask, and I just found those. I forget what they were. C2 was negative 1. C1 was 5, I believe. Great. So problem 2b asks, what is x of t? Well, x of t is just the first row of the general solution. So x of t is 5 times e to the negative t times 1 plus negative 1 times e to the negative 2t times 4. I know someone asked me in the discussion or the reflection how to find x of t and y of t. X of t is just the top row of this equation. Y of t is just the bottom row of this equation. So y of t would be 5 e to the negative t times 1 minus 1 times e to the negative 2t times 5. Simplifying this just a bit, we've got 5 e to the negative t minus 4 e to the negative 2t. Great. Part 2 of this says to find dx dt. So dx dt is the derivative of this. That's going to be negative 5 e to the negative t. Minus 4 times minus 2 is plus 8 e to the negative 2t. Please interject if you have questions. The next part says to find 3x of t, and so this is where it would have been confusing. So I really want to find 3x of t plus 4y of t. So, right, which is really, sorry, minus. So I have to do minus. So I want to find 3 times x of t minus, holy smokes, I keep wanting to write plus, 4 times y. Well, we already know what x and y are. X is just the first row of this. Y is just the second row of this. So that's going to be 3 times, okay, x of t, I've got it right here. It's 5 e to the negative t minus 4 e to the negative 2t minus 4 times y of t would be 5 e to the negative t times 1 minus e to the negative 2t times 5, which I'm going to write as minus 5 e to the negative 2t. Okay, and then when we add these together, well, let's see what happens. So I'm hoping it turns out right. So 15 e to the negative t plus 12 e to the negative 2t minus 20 e to the negative t plus 20 e to the negative 2t. And I made a small mistake here. That should be a minus 12, not a plus 12. And then when we simplify this, we get exactly, let's see, 15 e to the negative t minus 20 e to the negative t is negative 5 e to the negative t. And negative 12 e to the negative 2t plus 20 e to the negative 2t is 8 e to the negative 2t. They're the same, which they should be, because dx dt is equal to 3x minus 4y. So that's the point of doing this whole exercise here, is to actually see that, oh yeah, when you take the derivative of your solution x, yeah, Shannon, that was totally my fault. I wrote the wrong thing in the quiz. That was supposed to be 3, I had written in the quiz 3x plus 4y, but it was supposed to be 3x minus 4y. So if it totally went wrong, now you know why. Part 2c, though, should have still worked out, because y of t, the equation for dy dt, was correct. So you should have been able to show on the quiz for part 2c, you should have gotten that dy dt was in fact equal to 5 times x of t minus 6 times y of t. That part should have worked out. Anyway, I'll post solutions to this. Don't stress too much if you got it wrong, right? It's not a big deal if you got it wrong. But yeah, that's how this is supposed to work. So let's move along. Actually, let's go ahead and stick with this example just for a minute. Yeah, no, yeah, sure. Let's not. I changed it. So let's look at this other example I came up with. Where'd you go? Notes. Write stuff down. Notes. Yeah, let's take a look at this. So let's say we have this system of equations. dx dt is negative 3x plus y, and dy dt is x plus 2y. And the question that we're going to try and answer here is, what does the phase plane of this look like? So we should look at the eigenvalues, but like knowing the eigenvalues, like if you have one of those questions in your homework where you have like 4 different ones, you have to be like, what's this one's that, this one's that. You might kind of need maybe a tiny bit more than just the eigenvalues. So let's take a look. And this one might have terrible eigenvalues. That's life. So let's see here. Let's find I'm going to use the trace determinant method. So our matrix A is negative 3, 1, 1, 2. Someone asked me, how do I know when I should use the trace determinant method? And my answer is, I almost always use it unless it's super easy. Like if my matrix is like 2, 5, 0, 9, then you automatically know the eigenvalues are 2 and 9. But if it's not something where you have a 0 in one of those spots, I usually use the trace determinant method. So my trace here is negative 1, right? It's negative 3 plus 2. And my determinant is negative 3 times 2 minus 6 minus 1. Okay, so my eigenvalues are going to be negative 1 plus or minus the square root of negative 1 squared minus 4 times negative 7, all over 2, all over 2. That's going to be -1 plus or minus the square root of 29 all over 2. This is going to be terrible because I was not thinking, I was thinking of the nullclines instead of the eigenlines. That's all right. Actually, the nullclines are kind of what I wanted to talk about. So eigenvectors are going to be terrible here, but let's find them. So for, yeah, geez. Oh, I wonder if the person asking me really meant to, okay. I do think finding the eigenvectors, and maybe this is what the person in their reflection was asking me, I do think using the A minus lambda I method is a little bit more straightforward when you have gross looking eigenvalues. So if your eigenvalues are not nice integer numbers, I would generally recommend using the A minus lambda I times your eigenvector is supposed to equal to 0. That I think is a little bit easier when your eigenvalue is something terrible like this. Yeah, yeah. I'm not super psyched about it though. Well, let's do it anyway. So let's do the plus one first. So my lambda 1 is going to be -1 plus the square root of 29 over 2. We're going to plug that in. So we're going to get -3 minus -1 plus the square root of 29 over 2, 1, 1, and then 2 minus -1 plus the square root of 29 all over 2 times xy equals 0, 0. And while it looks bad, it's not so bad because you're just saying, okay, this times this is 0. So you're going to have -3. Let's distribute the minus in here. So it's really plus 1 minus root 29 over 2. That's going to be times by x plus y equal to 0. And solving for y is not terrible here. So you're going to get, sorry, I'm not, I have another one here. Y is going to equal the negative of this, so it's a +3. Sure. Minus 1 minus root 29 over 2 times x. That's gross. So my eigenvector here looks like the vector 1, and then the second component is 3 minus 1 minus root 29 over 2. That's kind of terrible. Okay. Here's the point I was trying to make, and I feel like I'm making it not as awesomely as I wanted to, is that now that you know that that's your eigenvector, and let's actually kind of, let's actually get a decimal approximation here. Where did I put my calculator? Sorry, the calculator here. So if I do 1 minus square root of 29 divided by 2, 3 minus that, I get about, yeah, calculator, about 5. So not exactly 5, but this is approximately the eigenvector 1, 5. Okay, why is that useful? How is it useful? Well, it tells me that if I'm looking for the graph of this thing, I know that on the line y equals 5x. Yes, the matrix is just the sum of the diagonal elements, which is the top left and the lower right. But so if I look at this eigenvector, which is approximately 1, 5, so 1 in the x direction, 5 in the y direction, right? I'm essentially looking like over 1, right? I'm like this. And so on this eigenline, we know that on the eigenline, well, the eigenvalue was -1 plus root 29 over 2, which is definitely positive. All the arrows point outwards, but more specifically, all the arrows exactly point in the direction of the line. So that's the important part I'm trying to get at. So for example, looking at this homework problem here just for 1 second. Where'd you go, homework problem? Let me share this one with you guys for just a minute. So on this homework problem here, this first one, it's asking you to match these systems to these equations. Well, if you look at this first system here, right, the eigenvalues are super easy to see. They're 2 and -2. And if you find the eigenvectors end up being 1, 0, and 0, 1. So if I look in the direction of the vector 1, 0, well, let's see. It looks like only this graph C, has an eigenvector in the direction of 1, 0, because, and I know you can't see them because they're not actually like drawn on there, but all the vectors that would be on the x-axis here would be pointing either purely left or purely right, which is the same direction. In a similar way, all the directions on the all the vectors on the y-axis would be pointing purely up or purely down because the eigenvector is 0, 1. On the other hand, I'm just going to try and look for another one. No, I'm not going to look for another one. Okay, so what I'm trying to say here is that you can find the graph of a system of equations or the corresponding phase plane to a system of linear differential equations by thinking about what the eigenvectors look like and finding the eigenlines. Let's look at, I think we could do one more example, sure. So let's look at something maybe slightly nicer, something that's easy to do. Like let's say our system of equations is represented by this matrix, 2, 0, 1, 3. So let's find the eigenvalues, we already know them. The eigenvalues are 2, let's make it a -3. So we know we're going to have what kind of system of, what kind of graph. We're going to have a saddle, right? Pointing in one way, pointing out another way. Let's find the eigenvectors. So this time, since my eigenvalues are so nice, I'm finding the eigenvectors in the other way, which is where we just say our matrix times our eigenvector equals our eigenvalues, our eigenvector. So this is going to give me 2x equals 2x. It's not super helpful yet. So I'm going to use the second equation, 1x minus 3y equals 2y. Adding y, I get x equal to 5y. So I could say that you could also solve for y if you really want to. Y equals 1/5 x, if that helps you graph the eigenline. My eigenvector is going to be x could be 5 and y could be 1. I graph the eigenline, I go over 1, 2, 3, 4, 5, and up 1. So on this line, all of the vectors exactly point in the direction of that line. Any other non-eigenline, right? Like so for, let me do one more thing. I'm sorry. Let's find the second eigenvector. So if this was a sneaky about it, if this was a instead of a 2, a -3, then I would have 2x equal to -3x. That would mean the x had to be 0, which means y gets to be 1. So our eigenvector is 0, 1. So in the direction 0, 1, which is the line x equals 0, right? We're here. And we're pointing in outwards. Oh, sorry, we're pointing inwards because it's a negative eigenvalue. But all the arrows on that line point in the direction of that line. Okay, let's also, while we're here, talk about Nullclines. So the Nullclines are just where each differential equation is equal to 0. I'm going to erase some, I can write some stuff back. So my differential equations are dx dt equals 2x plus 0y, and dy dt equals 1x minus 3y. Okay, so dx dt equals 6. If I set that equal to 0, I just get x equal to 0, which is also this vertical line. So this vertical line that's an eigenline also happens to be a nullcline. And here's what it means. Everything on this nullcline is going straight up or straight down because the change in x is 0. But here's what else it means. And I think this is kind of the key takeaway here. It means that everything everywhere else is either pointing either leftwards or rightwards. Right? If this is the only line where dx dt is equal to 0, then everything on one side of that line points rightwards, and everything on the other side points leftwards. In fact, everything on the right, everything on this side is going to point slightly to the right. So like things over here are going to be like that. Maybe then more like that. I don't know exactly, but it's a pretty good guess. And same thing up here, right? Things here are going to be pointing up and to the right. Now, let's find the other nullcline. And we set this one equal to 0. We get negative 3y equals negative x. We get y equal to 1/3 x, which is a little bit steeper than this. So it's kind of like this. So along this, and this is where it's a little more interesting. On this line, since dy dt is equal to 0, right, there's no change in y. It means everything is pointing purely horizontally. So over on this side, everything's going to be pointing purely horizontally to the left. I want to point out, notice that the arrows are not pointing in the direction of the line, like on an eigenline. They're pointing straight to the left. And over here, they're going to be pointing straight to the right. Okay. So what's interesting about nullclines is they totally separate the graph into sections where everything on one side points one way, everything on the other side, well, I should say, so everything above this line is going to point slightly downward, and everything below this line is going to point slightly upward. So like everything, right, everything here is pointing like this. You can see why we might use p-plane for this, right? Because actually trying to draw, it's kind of a giant pain in the butt. But also, right, that's why we also use our analysis skills, right? We knew before we even started doing this, lambdas were opposite values. That means we're going to have a saddle. So that's a good question, Lindsay. How do I know which direction the arrows are pointing for the nullclines? So I know that when dx dt is equal to 0, so I'm kind of also using the eigenvalue part. So for this one, especially because this one happens to also be an eigenline, when dx dt equals 0, I know that there's no change in x. There's no horizontal change. So everything is pointing either straight up or straight down. So for this eigenline, they're either pointing straight up or straight down. And also, sorry, for this nullcline, they're either pointing straight up or straight down. But since it's also the eigenline, and I knew it was a negative eigenvalue, I knew they had to be pointing inwards. On this nullcline, I know things are either pointing straight left, or sorry, straight to the left or straight to the right. And really the way, so really what you can do is you can either kind of look at the graph and say, well, I know things on this side are pointing to the left because over here on this side of things, x is negative and dx dt is 2 times x, which is going to be negative. So over here on the left, dx dt is negative, which means you have to point in the leftward direction. Over here on the right, dx dt is positive, meaning pointing in the rightward direction. In a similar way, if I'm above this line, y equals 1/3 x, so like I'm at the point 0, 4, well, x is 0 and y is 4, dy dt is negative, which means I have to be pointing downwards. On the other hand, if I'm down here below this nullcline, I have to be pointing upwards, because if I'm like at the point, say 0, -3, x is 0, y is 9, sorry, y is -3, which means you get 9, you have a positive dy dt, which you're pointing upwards. So really, I'm just doing some sign analysis, right? I'm looking, okay, where is this positive? Where is this negative? Wherever this is positive, you're pointing up. Wherever this is negative, you're pointing down. Where is this positive? Where is this negative? Wherever this is positive, you're pointing to the right. Wherever this is negative, you're pointing to the left. Okay. So let's see, there was something else. Oh yeah, I want to talk about compartment models. Let's talk about compartment models, which I don't think is actually super, I mean, it's in your textbook, but they don't actually use those words in your textbook, which is kind of annoying, but fine. Also, you guys said you wanted to, sorry, one second. Yeah. So let's look at, yeah, I think, so here's a very typical kind of compartment model setup. This is very similar to what's in your homework. So let's look at this one here. Let's say we have this sort of thing here. X, we have Y, and we are given that stuff is going out of X at a rate of C times X, and stuff going this way and that way. It is important which way the arrows point. Leaving X at a rate of A times X, and coming into X at a rate of B times Y. And then also we're leaving Y at a rate of D times Y. This is kind of your standard compartment model where you have X and Y, things going between X and Y, and also you're losing stuff from X, you're losing stuff from Y. And X and Y can represent a number of different things. It can be some sort of absorption rate, or your, I mean, like, I will admit I'm not so great with the biology stuff, but I know he was talking about it in class today where you've got like something being absorbed into a system or losing it some other way, and this is kind of model that. But here's the system we're given. We're given that, say, dx dt is equal to, what have I got here? I'm going to make up, no, let me use the numbers that we're given. Negative 1.7x plus 1.6y. And dy dt is equal to negative 0.7x minus 2.91. Okay, well, the idea is we're supposed to find A, B, C, and D by using the fact that we actually know how to write the differential equations in terms of A, B, C, and D. So if I'm thinking about what dx dt is, so dx dt is, well, we're adding, so it's the rate of change of x. Well, x is increasing, well, we're putting in b times y. And so we use so it is important to write the x's and y variables in the correct order. We're always writing x before y since the x equation is first, the y equation is second. Let's start with the x stuff. So as far as x is concerned, we're losing c times x and a times x. So we're losing a plus c times x. We're losing it, it's in minus, right? Our rate of change is negative because of that. But then we are gaining b times y. Great. For dy dt, we are gaining ax. But we are losing by and dy. Well, that leads us to some equations. In fact, it's really easy to find a and b. B has to equal 1.6. And a has to equal 0.7. Sorry, negative 0.7. Then we can find b and d. Let's see. So, or sorry, c and d. So I can say that a plus c has to equal 1.7. But then I know that a is negative 0.7. So negative 0.7 plus c. Like, and I was like, I feel like I've made this one. So I noticed I might have made a mistake because I was like, it seems weird for that. Like, I feel like all these numbers should actually be positive because the rate you're talking about, the rate that stuff is leaving as a proportion of what you have. And the thing I made a mistake was I actually wrote down as clearly I'm off to doing. Actually, I wrote a negative sign there. Sorry about that. So a should actually be positive 0.7. Sorry about that. Which means C should be +1. And then similarly, we can find D by saying that B plus D equals 2.9. So B plus D equals 2.9, but B is 1.6. So D is going to be 2.9 minus 1.6, which is 1.3. That's how we can find all those coefficients. So I want to be super clear though, right? It's not that A, B, C, and D are just equal to the coefficients of X and Y in each of these equations. A and B are, but C and D you have to work a little bit harder to find. Yeah. Let's look at another one. And then we'll look at a harder one. He did say your test is going to be on Friday. That means we're going to have a practice test on Wednesday, like we did last time. I will try to write some questions that are more in the vein of what he is writing, where there's a little more interpretation to do. Which I tried to do last time, right? The questions I got were actually old questions of his, but I will try a little harder to make the questions a little more like what he would write. But yeah, I'll do my best. So let's look at the following. Let's look at this model. So I've got X, got Y, I've got things going out of X. So it's going out of X at 0.1X, coming into X at 1Y, and let's make it 0.9Y. Going out of X at 0.4X, and going out of Y at 0.6Y. Okay, so we want to find the model, and then we want to determine what the equilibrium is. This is a sink, a source, a saddle, et cetera, et cetera, et cetera. So let's see here. So first of all, the equations. So I know that dx dt, we're losing 0.4x and 0.1x, so we're losing 0.5x. We're gaining 0.9y. dy dt, we are gaining, so I'm always thinking x first. So right, the x's are gaining, so we're gaining 0.1x, we're losing 0.6 and 0.9, so we're losing 1.5y. Great. So my matrix is negative 0.5, 0.9, 0.1, negative 1.5. This is definitely a time where the trace determinant method is probably what I want to use. Even then it's going to be not super nice. So the trace of this matrix is negative 0.5 minus 1.5, which is negative 2. Actually, that happened to turn out to be nice. The determinant, on the other hand, so negative 0.5 times negative 1.5 is is positive 0.75. Minus 0.9 times 0.1 is 0.09, which is going to be 0.66. Okay, so let's figure out what the eigenvalues tell us. So I'm probably not actually going to find the eigenvalues. I'm probably going to just get close enough that I know they're real or imaginary or whatever. So I guess we can put them up here. So my eigenvalues are going to be, so trace negative 2. So already I know that, actually I don't know anything quite yet. And actually I know a couple things. I know they can't, oh no, that's not true either. I don't know anything yet. They couldn't both be positive. That's the only thing I know. Right? No matter how big this is, negative 2 minus something will be negative. So we definitely don't have a source. Well, let's see. Negative 2 plus or minus the square root of negative 2 squared minus 4 times 0.66. Okay. All over 2. So let me ask you guys, are my eigenvalues real or complex? Give me R, or, and it totally depends on what's going on in this square root here, right? Is the stuff in here positive or negative? Meaning, is the thing real or complex? Totally, Ethan, right? 4 minus 4 times 0.66. 4 times 0.66 is less than 4. 4 minus number less than 4 is going to be smaller, or is going to be positive. Great. So we know they're real. Now the question is, are they, what do you get, where do you get the value for the quadratic formula without a function? So this is something I've talked about a few times, Max, where, I'm going to erase this, where you can find the trace of a matrix, which is just the sum of the, so here's what it really is, Max. It really is the quadratic formula. It's just that there's this thing for 2 by 2 matrices. It says whenever you find the determinant of A minus lambda I, instead of doing all the work, it's actually always true that the determinant of A minus lambda I is equal to lambda squared minus the trace, times lambda plus the determinant. That's always true for a 2 by 2 matrix. And so then if we're setting that equal to 0, if we use the quadratic formula is going to tell us that the lambdas are negative b plus or minus the square root of negative b squared, or b squared, either way, doesn't matter, you're squaring it, minus 4 times a, which is 1, times c, which is delta, all over 2 times a. Oh, look, it's the same formula. So it's actually, we're using this trick that says that's what's happening. You're welcome. I'm sure you're not the only one that had that question. So that's the trace determinant method, right? That's why you can just say, I don't need to write out this characteristic polynomial, which is what that's called. I'm just going to say, I know the trace, I know the determinant, I know where they go in the quadratic formula. Okay, so we know everything's real. They can't both be positive because you have -2 minus a thing. Are they both negative though, or are they both, or are they opposite signs? Well, that's where so this is -2 plus, is this number bigger than 2 or smaller than 2? Well, that number happens to be smaller than 2. So you've got 4 minus a number. Square root of 4 minus number is going to be smaller than 2. -2 plus a number that's smaller than 2 is going to be still negative. So they're both negative, which means we have a sink or a stable node. And I will also point out, this is where doing the analysis with that little graph thing I showed you guys last time would actually be super duper helpful. So we know that, right? So if this is your trace and this is your determinant, down here you're in saddle land, where your determinant is negative. And then up here, you're in either node land, where your trace, where basically your eigenvalues are real. So tau squared minus 4 delta is positive. Or you're up here in spiral land, where tau squared minus 4 delta is negative. Well, we know that we're definitely not in saddle land because our determinant was positive. And then we also know that we're not in spiral land because we saw that the insides of our square root here were positive as well, right? It is true for us that we even said this, right? Tau squared minus 4 delta, tau squared minus 4 delta is positive. And then we're on the stable side of things, where tau is negative, not the unstable side of things, where tau is positive. So we could have done it that way as well without actually even calculating stuff. We could have had calculated determinant trace, right? We're like, oh, determinant is positive, not a saddle. Trace is negative, meaning we're on the left side. So it's either a stable node or a stable spiral. But we know it's not a spiral because we know that the eigenvalues have to be real. Okay. In the vein of trying to do examples that are more like kind of the more biologically involved examples he likes to do, I'm going to grab one of these questions from the textbook and we'll kind of go through it. There's always a lot of things you can say about a system of equations, right? Like we could have found the eigenvectors and talked about the phase plane, but we're not going to. So let's look at this. This is question 6 from chapter 10.3 about radioimmunotherapy. Let me read some things here to you. It's a cancer treatment in which radioactive atoms are attached to tumor-specific antibody molecules and then injected into the blood. The antibody molecules then attach only to tumor cells, where they then deliver the cell-killing radioactivity. The following model for this process was introduced in the previous example. Here it is. So dx1 dt is equal to negative ax1 minus bx1, and dx2 dt is equal to bx1 minus cx2. And they want us to first, and so all the constants are positive. So a, b, c greater than 0. X1 is the amount of antibody. And in the blood. And X2 is the amount of antibody in the tumor. So they want us to find the general solution. Before we find the general solution, let's draw the compartment diagram. So again, X1 is the amount of antibody in the blood. X2 is the amount of antibody in the tumor. So let's see. So let's look at X2 first. What's going into X2? Looks like B times X1 is going into X2. None of X2 is going into X1, which makes sense, right? We shouldn't have the antibody that's in the tumor going back into the blood. That's not the way things are working. What we also have, though, is, right, we're also losing A, X1. I don't know exactly what that's, and this was set up before, so I don't know exactly the situation. And then we also have dx2 is losing cx2. So that's how I would draw the diagram for that. Let's go ahead and solve the system. So, right, this is going to be a little bit more challenging to solve because we're just given letters A, B, and C, right? So let's write our matrix here. Our matrix is going to be, so, right, coefficient of X1, coefficient of X2. So the coefficient of X1 is minus A minus B. Coefficient of X2 is 0. In the second equation, the coefficient of X1 is B. Coefficient of X2 is negative C. Okay, well, we can certainly find the eigenvalues right there, right there. We can write some stuff here. So the eigenvalues are negative A minus B and negative C. Well, that's not too terrible. So then we're going to find the eigenvectors, right? Because we're trying to find the general solution. We need the eigenvalues and the eigenvectors. So the eigenvector, let's find the first one. Negative A minus B, 0, and then B minus C times my eigenvector should equal this eigenvalue times the eigenvector. All right, so I'm getting negative A minus B times X equals negative A minus B times X. That is not super helpful. So let's look at the second equation. Bx minus cy equals negative A minus B times y. Well, we can solve that, and we kind of have to. So let's see. So I'm going to add that to over here. So I've got bx equal to c minus a minus b times y. So my eigenvector could be that y is equal to b and x is equal to c minus a minus b. Fun. Let's find the other one. So then we're going to use the second one, lambda 2 equal to negative c. Let's go over here. We're going to have negative a minus b 0, b minus c times xy equal to, now instead of being negative a minus b times, it's going to be negative c times xy. Sorry, I know I stuck that in there. Let's go ahead and use the, sure, we can use the first equation. So negative a minus b times x plus 0y equals negative cx. Okay, everybody should be able to tell me, what does x have to be in this equation? So I've got a number times x equals a different number times x. The only thing x could be is 0. Which means y has to equal 1. Or whatever it would be like. I'm going to pick 1. So my second eigenvector is 0, 1. How much more or less exciting? Okay, so then our solution to this system, and look kind of bonkers, only kind of. So we've got x1 and x2. So x1 of t, x2 of t is going to equal c1e to the lambda 1, which is negative a minus b, times v1, which was terrible, right? It was c minus a minus b. Plus c2e to the lambda 2, which was negative c, times, was it 0, 1? Yeah, 0, 1. All right. That would be our very general solution. And then if we're given the initial conditions that both x1 of 0 is 0 and x2 of 0 is 0, which again makes sense, right? If we're talking about starting antibody treatment, it would make sense that before you start doing it at time 0, you have 0 antibodies in your blood and 0 antibodies in your tumor. So using those conditions, let's solve for C1 and C2. Okay, well, so my top equation will be 0 equals C1 times C minus A minus B plus C2 times 0. Okay, so it looks like C1 is going to be 0. That doesn't seem very good or exciting. And if x2 is 0, then we're going to have 0 equal to c1 e to the, oh, you know what? I forgot my solution. Forgot the t's. Which is why you get a 0, an e to the 0. But for x2 of 0 being 0, you get 0 equal to c1 times 1 times b plus c2 times 1 times 1. So, oh, interesting. But c1, I feel like something went wrong here. It does not feel right that both c1 and c2 should be 0, which is what I'm clearly getting. So it makes me feel like there's probably a small mistake somewhere. So this is, I know, so I apologize. It feels like it's kind of been a mistakey day for me. Not my best. But what I want to point out is that when you get to a place and you see that the answer doesn't make sense, you're like, it doesn't seem right that my general solution should be x1 and x2 equals 0 all the time, which is what it would be if both c1 and c2 were 0. It seems wrong. I feel like we should look back. I know it's 2 o'clock. Give me just a moment. Let's look back for a second and make sure we've got things right here. Now my eigenvalues are definitely correct. Yeah, negative. Yep. Okay. Eigenvalues are right. Let's check out lambda 1 equal negative a minus b. I feel like that could have been where I made a mistake. So when I do this times this, you get negative a minus b times x equals negative. Okay, cool. When you do that times that, you get bx minus cy equals negative y. Bx equals c minus a minus by. If x is b, sorry, if x is c, no, that works. Y is b. Okay. And then over here, if we have our eigenvalue being negative c, which it should be, we get x has to be 0 and y gets to be 1. That works too. Okay. So then this, let me see if I've made some other dumb error. No, that was right. That was right. That was right. Oh. No, I guess that answer does make sense. Right? If we why does this answer make sense? If you're starting at 0, 0, you're starting at the equilibrium. And since, well, actually doesn't really matter, right? If you start at the equilibrium, you can't change. If your derivatives are both 0 because x1 is 0 and x2 is 0. This is number 6 in section 10.3. But so I want to point out, I didn't make a mistake, which is good. I just wasn't thinking about how to interpret things correctly, right? If you start off with the initial conditions being both 0, and that means nothing can change. So if you've already got zeros, it's going to stay 0. So that's what's happening. If you had a different initial condition, and it seems like kind of a, it seems, I read it wrong. So the initial condition was actually, sorry, so what happens when you're trying to read stuff, was that x1 of 0 is not 0, but x naught. So if that was actually what we had, sorry guys, I don't mean to make mistakes, but sometimes they just happen because you read the thing wrong. But if x1 of 0 is x naught, you'd have x naught equal to c1 times this plus c2 times 0. So then you would get c1 equal to x naught divided by c minus a minus b. And then solving this, you would have c2 equal to negative c1 times b, which would be equal to negative b times all of this. So negative x naught b over c minus a minus b. Okay, that makes more sense now. So it's really important to read the question carefully, as I hope I've demonstrated very clearly today. C1 here, that would be this value here, and C2, that would be this value here. Okay.